but I have changed the topic to talk about turbulence and the Cracknell model later, maybe sometime later, because this is what I'm going to talk about today is something we have been involved in actually trying to solve for some time. And I think we have some ideas about how to attack the problem. But I will give you a slight background of why we are looking at this kind of problems. So what we had actually, clearly had actually done simulations of what is called a magnetic buoyancy instability.
Are you going to switch on? Gustav, are you going to switch on Axel?
He's already there. Oh yes, he wanted to early.
No, he just asked me who was going to Skype.
So maybe we need another laptop.
I can bring mine.
Okay, I will just talk about the magnetic buoyancy instability.
I thought he's already there. That's why I was asking you.
Okay. So this is basically
recording it. Okay.
a simulation with layers.
You can't do both at the same time.
So we have a density stratification rho as a function of z.
Okay.
Gravity is acting downward. And the situation is such that this is stably stratified. To such a situation, we introduce a magnetic field in a thin layer and a very strong magnetic field compared to the rest of the parameters in the problem. And the motivation is basically the sun, because in the sun, one of the pictures of the solar dynamo is that there is a strong magnetic field sitting at the bottom of the convection zone, which rises to the convection zone and creates the sunspots. So this is kind of a toy model of that. And such a magnetic field is buoyantly unstable. It rises through the system. And such a rise actually creates turbulence in the system. So this is the basic problem we wanted to study. Okay. Now the problem has been studied quite a long time back. But the particularly interesting thing that we found is the following. So what is often done, in addition to such a situation, one also have rotation in the problem. And under rotation, the system can turn out to be helical. This is kind of a picture of the, so let's say this is the sun, the convection zone of the sun. And then we can imagine our box to be sometime here and sometime here.
Hi Axel, are you?
So we have.
So maybe I should switch on the
and
video here so
rotation
that.
acting this way. So
Can you see
in the
anything?
same system, I can mentally move it all around here by changing the direction of gravity. So I can do it this way and do it this way. And depending on the dot product of omega and g, I can create a quantity which is basically a pseudo-scalar. So I can generate helicity into the problem. Now the question is, what happens at the equator? At the equator, there should be no generation of helicity. What we found out from our problems was that at the equator, it is possible to generate helicity if the initial condition has very small amount of helicity. So this is what we were calling breakdown of parity. So this is something we have been trying to understand. And so that's what we shall try to do by the multiple scale method. But I will go back to the very elementary things first and describe them, and then come to the main problem that we are looking at. Okay, so the thing we are going to discuss is the technique of multiple scales. And let's pick, I'll basically do this by doing examples. So let's pick a particularly simple example. So what we have is what is known as the van der Pol oscillator. Okay, so this is the Van der Pol oscillator. So if we drop the two middle terms, we basically have the harmonic oscillator. To that we add a dissipation. So that's the damped harmonic oscillator. And then finally we have a nonlinear term into the problem. So that's the Van der Pol oscillator. So now interestingly, if we have lambda greater than 0, then we can actually have a growing mode into the problem. So basically we can have a growing mode into the problem. And let's see that by first doing a linear stability analysis. So we change u to u plus delta u, some u0 plus delta u, and the initial u0 we take to be 0. Okay, so of course this will be delta u double dot and u0 squared is of course 0. So we can drop this down. Right. And then we try to look for growing or decaying solution. So we say this is of the form exponential pt. So once we put that back into the problem, we basically have a polynomial solution. Right. So then this obviously is a quadratic equation we can very easily solve. Okay, so far so good. The linear stability tells us that there is a growing mode in the, it's possible to have a growing mode in the problem, and the growth rate is equal to lambda. And it also tells us a few more things. So firstly this is linearly unstable. But depending on whether this quantity is positive or negative, we can actually have complex roots or not. So basically, let's now say that we mentally increase lambda from negative to positive. So let's say lambda is some small parameter times mu, where epsilon is a small parameter. Okay, actually, let's go into that a bit later. So you can see it's possible to have actually imaginary solution. So that basically means that you can actually have oscillatory solutions here. So in principle, for example, for lambda less than 0, you can think that the phase diagram in this case will actually give a fixed point, which is actually u equal to 0 and u dot equal to 0. Right? Now, this is for lambda less than 0. This is what we get from the linear stability. Now for lambda greater than 0, we can see it is possible to have oscillatory solutions. So in principle, we can get a limit cycle. So So as lambda goes through 0, we can get a bifurcation which takes us from a stable fixed point to a limit cycle. So that's what is known as the Hopf bifurcation. So this is kind of what we can roughly see, because you see, as soon as the mode starts growing, for large enough delta U, the nonlinear term will become important, and that will kind of saturate the problem. So to see if that is at all possible, let's look at the total energy. So total energy as a function of P is U square plus U dot square. Yes, that should be. Right. And then the time derivative of that. So let's replace this from the equation, which will basically be so actually we can have a steady state in the problem, the total energy derivative of that to be equal to 0, if we have a situation where U squared is of the order of twice lambda. So if we kind of, so once U starts growing and reaches amplitude of the order of square root of lambda, we can actually get a saturation coming from the nonlinear term in the problem, and that can actually gives us steady solutions. So kind of the mental picture is that we have a growing mode which can become unstable, and then the unstable mode will saturate and will saturate into a limit cycle. So we can in principle have a Hopf bifurcation. So now the question is how to see all this in a mathematically consistent way. So to do that, let's do a systematic perturbation expansion. So of course, we first need to introduce some small parameter. So you see the problem is very well understood when lambda is less than 0. So I guess, and that's when the nonlinear terms are not important. So we would guess that the nonlinear terms would start becoming important as lambda goes slightly beyond 0. So let's say lambda is a small parameter times mu. So I'm just rescaling lambda. Okay. Now we have seen that as lambda goes through the transition, U actually scales as square root of lambda. So then the other scaling which should involve the small parameter will be the following. So we will do a change of variable which will just change the scale of U. So mu is an order 1 quantity where lambda is order epsilon. We will define a new variable which is an order 1 quantity where this will be order root over of epsilon. And right, so let's look at the growing mode P, which in this case will be epsilon mu plus minus, and then for small epsilon this is epsilon square, so we will ignore terms of the order epsilon square. So we just have I omega naught. So that's where the Hopf bifurcation comes from. So this is as epsilon goes to 0 from the positive side. So we consider a case where epsilon is much smaller than omega naught, of course. So you see in this case what is happening. If you now think about the growing mode, so we are slightly above the criticality, and the criticality is lambda equal to 0. We have a growing mode whose growth rate is given by epsilon, and epsilon is small, so it's a very slowly growing mode, and a fast oscillating mode. So we have been able to, in some sense, decompose the problem into a slow time scale and a fast time scale. So that's the idea of the problem. The idea of the multiple scale is basically based on trying to pose the problem in a way that we have a scale separation into the problem. So that's clearly possible when we are slightly above criticality. And then we have these two scales. So what we will then try to do is first scale our time such that we can now decompose time into a slow time and a fast time. Then we will try to integrate over the slow time to write an effective equation for the fast time. This whole scheme will be particularly easy for this equation because this is a simple problem for such kind of an approach. We don't have, the mess will start once we go into the real equations, which will be the hydrodynamic equations. But let's do that slowly. But the idea is, the basic idea is this. Given the problem, first do a linear stability. That in hydrodynamics is a problem in its own right. Once you do the linear stability, you know what those growing modes are and what are their structure. That kinds of tell you where to start the perturbation expansion from. And that will also tell you the kind of scaling of variables you need for your perturbation expansion. Once you know them, you can start doing it.
Can I ask one question?
Yes.
I still don't understand the difference between lambda greater than 0 and less than 0. And how do you...
For lambda less than 0.
For lambda less than 0, it is a decaying mode,
Yes.
clearly, right?
Yes.
So we don't have to worry about that.
Yes, for a decaying mode, at large time, u is 0, u dot is 0.
So, okay.
So that is the phase diagram here. See, this is a u dot phase diagram. So wherever you start in this plane, at large time you will end up in the origin. So the origin is a stable fixed point. On the other hand, in this case, you can actually have an oscillatory solution, right? Which will be it need not be a circle. It can be an ellipse, but it has to be a closed curve because it's an oscillatory solution. Yes.
But I mean, what's the physical meaning of having lambda smaller than 0?
Lambda is 0.
Lambda larger than 0. What's the point?
Do you mean what's the point? It's you are thinking that
the dissipation term, then lambda. I mean, in that case, lambda has to be positive.
You are basically thinking that this is a physical dissipation into the problem, right? But take this problem as a representative of some other problem. Say, for example, you are looking at a hydrodynamic problem. When you look at linearly stable hydrodynamic modes, for example, let's say you are looking at a Rayleigh-Bénard problem. And then the controlling parameter of the problem is, for example, the Rayleigh number. Now you know that for very small Rayleigh number close to 0, nothing will happen. Because the temperature difference across the plates, say, is 0. So nothing will move. So the fixed point is just the origin. Now as you increase the Rayleigh number, you know that there will be growing modes. Modes which can grow exactly like this. Right?
You always need some kind of driving.
No, the driving is coming from the temperature difference. Right? In the Rayleigh-Bénard problem, the driving is coming from the temperature difference.
What's the temperature difference in the equation?
This is not the Rayleigh-Bénard problem.
I can't see why you should increase.
This is a simple problem. I mean, in principle, just take this as a mathematical problem.
Well, it's a damn oscillator.
Yes, but take it as a mathematical problem and change the sign of lambda.
And it blows up.
No, because this will saturate it. That's the main point. And this can happen in electric circuits. This is not strange at all. Van der Pol oscillator does come up in electric circuits quite frequently actually. This is a well-studied problem in nonlinear dynamics. So see, it's a growing mode, but this will saturate it. Right? You have a nonlinear term into the problem. So the main purpose of taking this equation so that we have an oscillatory mode and a growing mode and something to saturate them. It's kind of a bare backbone problem.
So usually many times one takes averages of the first mode and then
Yes.
decides the slow motion.
Yes.
Why do I want to do the opposite?
No, I exactly want to do that. Average over the first mode to write an equation for the slow mode.
Oh, you said the opposite.
Oh, I'm sorry. No. Sorry. Utterly stupid. I want to say that I average over these, the first varying modes, to write an equation for the slow modes. But in this case, this will be too simple. We may not have to even do an averaging. We may be able to exactly solve for the slow modes. We will see. But yes, sorry. Shall I say everything again?
No.
So we have a growing mode which is growing very slowly. Right? The growth rate is very slow, whereas the oscillations are very fast. So we want to average over the fast oscillations to write an equation for the slow growth rate. That's the idea.
Is this what you mean by multi-scale?
Yes. So
But
this,
it's two scales.
yes. But there is a scale separation. In principle, you could have, if you had lots of frequencies, but they all were periodic up to a certain frequency omega naught,
Okay.
then things would have been perfectly fine.
Omega naught is the lower limit.
Omega naught is kind of the
As in
lower
all
limit.
frequencies are higher than omega
That's the
naught.
frequency up to which we average. So that's the idea. Okay. So till now our time has been tau. So let's now make the following substitution. So this is the fast scale and this is the slow scale. As epsilon is very small, you can see that, for example, this has to change by huge amount to make a small change in this one. So let's, for example, not think about it for the time being. So when the fast time scale changes by huge amount, the slow time scale changes by very small amount. So that's what the epsilon is doing here. This will imply so then let us just put each one of those terms and see what it looks like. So in the time. Now things start becoming nasty. So we have to be really careful. This will become this one, epsilon, and this one, epsilon squared. So now let me do it term by term. Space here. Okay. So then we expand the variable itself in a perturbation series in epsilon, and then put this back and start collecting terms. So clearly all hell breaks loose. In pencil and paper, this is not a big problem. It's actually fairly simple. So we have terms like u0 plus epsilon 1 and then where is epsilon? So this 3 comes from the first term. Then we look at the second term, which is minus twice mu epsilon. So let's say then you look at this derivative. So each derivative will give you 1 del del t and 1 over the slow time scales with another factor of epsilon. So just follow this prescription, plug it in 1 by 1. So then you have this one. There is already an epsilon here, and this will be the mess. And then this has to be multiplied by this. So this is the nonlinear term when I take the derivative with respect to the first time, and then there is the nonlinear term when I take the derivative with respect to the slow time. And then more terms. So it's a pain to write them all, but it's somewhat useful because then you understand the amount of pain one has to go through. So then basically just one term is left. That's the omega naught square. Plus then you have omega naught square So all these put together equal to 0. So then let us try to actually collect terms in different orders of epsilon. Now to the 0th order in epsilon, we just have this one. So 0th order, we just have and then everything has epsilon in it except the last term, which gives us, okay, so that's just the harmonic oscillator, which will have an easy solution. So u0 as a function of t will be some a plus its complex conjugate. Now note that each of the variables now are a function of the slow time and the fast time. So u0 is a function of t and also the slow time. So this slow time dependence is the one that goes over to a. So basically we solve this and then we assume that this will be the kind of solutions we are looking for. Now you see this is basically the frequency of the linear oscillations. Now as we have nonlinear terms, in principle we can generate new frequencies by interaction between them. And we will see whether such a thing is possible or not for this particular problem. In general, of course, it is possible. So at present we just have an amplitude which depends on the slow variables. Okay, so let's now look at the next order. So we have epsilon to be 1, and then so we have this one. So once I collect them, I get something like this. So here the interesting thing is that let's collect everything with u1 together. Then we have an equation okay. So this one, you can again think of it as another harmonic oscillator, but now with a forcing term. And the forcing is coming all from u0. Okay, so we know the solution of u0. Let's just plug it back here. So once you plug it back here, so this becomes minus 2 I omega naught to the I omega naught t plus I omega naught e Now don't forget the complex conjugate here, and to get the u0 square, multiply them properly. So there is a and there is a star e to the minus I omega naught t So these two multiplied and with this factor will give you a term of I omega naught a modulus square e to the I omega naught t. Then this one with itself will give you a term of I omega naught a cube e to the thrice I omega naught t plus complex conjugate. Okay, so now you see the obvious thing is that this is a harmonic oscillator which is being solved by a forcing at exactly the same frequency. This term is at thrice omega naught, don't bother about it now. All the other forcing terms are exactly as the omega naught frequency. So that basically will give us resonance and complete unbounded growth of the solution, which of course we cannot allow. So for the solution to exist, for unbounded solution to exist, we must set all the terms which multiply e to the I omega naught t to 0. So in this language, that is typically what is known as the solvability condition. So the solvability condition, if we start collecting terms, will look something like this. So after so much of mess, we have actually found out an equation which is quite nice. So it basically tells you that A, the amplitude, sorry, this is of course the slow time. Even on the slow time scale, it actually grows by the same growth rate mu. That's of course obvious because the whole mode is actually growing at the rate of epsilon mu. And this time scale is epsilon times the usual time. So in this time scale, this just grows by the growth rate mu. And then there is a saturation coming from there. So in general, this type of equations can have the more general form, which is dA dt is minus, but beta can be a complex number. So if beta has an imaginary part, so for example, you can take this one, A is of course complex, and then you can write A as its basically amplitude and a phase. So let's say A is R e to the I theta, and then you can write one equation for R and one equation for theta. And in this problem, this is 0. And this will of course have something here. Whereas in general, this will actually multiply the imaginary part of beta. So if you now think about what A actually multiplied, A multiplied the solution of U0. So if A itself has an imaginary part, that will actually, I mean, if there is a phase that is changing, that will actually give you another frequency in the problem. So if in some problem you get an equation where beta is imaginary, your linear modes are actually interacting to generate new frequencies into the problem. Otherwise, it's the same frequency that is remaining, but you have a saturation here. So that's the general situation. So the important thing is to notice the solvability condition. Now that we have worked through this toy problem, let's worry about the actual problem. So I am not going to work on the actual problem as I have done here. The toy problem is easy to do. So first let us look at Rayleigh-Bénard convection. So we have two plates. This is the distance d. This is say x-axis. This is the z-axis. This is cold and this is hot. Right. So we basically have a fluid inside two parallel plates, infinitely long. And then I have defined my axis. The thickness is d. And then let's start working in what is known as the Boussinesq approximation. So the equations in the Boussinesq approximation are first that divergence of u is 0. Second is the Navier-Stokes equation. So I have non-dimensionalized them. So we have the Prandtl number and the Rayleigh number. So the Prandtl number is the ratio of the diffusivity of the, basically the fluid viscosity and the diffusivity of the temperature, where the temperature is theta. The Rayleigh number is this one, which basically determines whether we are going to have convection in the system or not. And then the equation for temperature.
Is there an alpha there? The expansion?
Yes, here. So basically we assume that the coefficient of linear expansion is actually alpha.
How is that an expansion if it's incompressible?
Sorry?
How is that an expansion if it's incompressible?
It is incompressible.
This
Boussinesq
is
approximation.
The fluid is essentially incompressible, but there's one exception.
Basically you take a density which can...
Deviation from the background density only there. That is inconsequent.
I mean, this is...
Density is the constant background. But this is just this approximation.
The Boussinesq approximation is basically quite well. This is just standard. And it captures most of the physics, at least as far as Rayleigh-Bénard is concerned. It's quite difficult to do a theory without it actually. Okay. So as we said earlier, the first thing we need to do is to do a linear stability of this problem. Then we know what are the linearly unstable modes. And then we need to do an expansion in multiple scales. And that is going to tell us what is going to happen to this, really happen to this problem. So for linear stability, what people often do, I'm not going to go through all this. I'm just going to, and because the linear stability and this Rayleigh-Bénard problem is found basically in all books. So it's quite standard. It's in Chandrasekhar, for example. So I'm just going to take the linear stability results as given and then start from there. So the idea is, let's say the easiest way to do it is to take the velocity as three components of velocity as u, v, and w, and also take and one can show basically that the linearized equations look like this. where this one is actually the horizontal gradient. So let's say these are the.
That's omega, the what?
That's
the vertical velocity.
Yes. So yeah, then we need to of course worry about the boundary conditions, but let's postpone that for a little while. So then we basically decompose them as some function of z, and then in harmonic modes in the horizontal direction. Okay, so this is basically exactly the same kind of ansatz I have been making in the oscillator problem. So I'm basically trying to look. So the whole problem can now be reduced to the following. I will plug this back into the equations, and then of course del squares will be k squares and things like that. And then I will get a relationship between the k and the sigma, where sigma is the growth rate. So then which will of course also involve the quantities like Rayleigh number and the Prandtl number. So then I will look for the case for which k there is a fastest growing mode, for which k sigma is biggest. But of course before that one has to look for exactly which situation sigma is positive at all. So you have to first look for positive sigma. That will correspond to a critical Rayleigh number, and then at that critical Rayleigh number we have to look what is the critical Fourier mode, exactly which mode goes unstable, and then our analysis starts.
What in convection, what would be the faster mode, for example? You say that there are modes varying in different time scales. In this case, what is the...
No, this one, for example, will give a growing mode for some Rayleigh number.
Yes.
Which will be the critical Rayleigh number.
And then it will saturate.
Then it will saturate. But the saturation is completely outside the domain of linear stability. So that's one thing. Secondly, what we will see is that it's not that just one discrete mode become unstable. What happens is that there is a band of mode which becomes unstable. So
with different time scales.
No, all at the same growth rate, roughly. So there is a whole band of mode which goes unstable near the critical mode. So you cannot really say that the linearly stable solution will be found, because as soon as the linear stability sets in, there will be competition between different modes. They will interact with each other, and the nonlinear part needs to be taken into account. So depending on the exact system, depending upon how slow you are doing your simulations, you may be able to see a linearly growing mode or not. A linearly growing mode can be present for a very short instant before nonlinear interactions can completely change it or slightly change it, or depending on what kind of amplitude equations we can write for them. So again, we will basically, the growing modes will have a situation where, so once we know sigma, we will scale our time by that scale, so that we will look for what happens if we take the fast growing mode out of the problem. How do they behave beyond that time scale? Just what we are doing here. So this, for this problem, look at Landau-Lifshitz or Chandrasekhar, for example. Chandrasekhar does all the nasty calculations to great detail. So either of them will do pretty well. So the boundary conditions we often use. So we say that the temperature fluctuations at the boundary are 0, and then we say that the vertical velocity at the boundary are also 0, and then we impose stress-free boundary condition, which will imply that del u del z equal to 0 and del v del z equal to 0, where u and v are the x and y components of velocity. So with that, if we use incompressibility, then we have this. Take another derivative with respect to z and then interchange the order of derivatives. So this and this are 0 by the virtue of this relation. So we have this additional one. Which basically gives us this. So the stress-free condition can be translated into this boundary condition on W, which can be satisfied by saying that the following ansatz is true. So we took Wz and then we write Wz as some W0 sine n pi z by d. Sine n pi z. And then theta is some theta 0. So let's use those ansatz. And once we put them back in this, so that the time derivative gives me a sigma, and then I get a k horizontal square from the del square plus n square pi square times W0, which is triangle number, and that grad 4 is del square square. So that is just k horizontal square plus n square pi square whole square times W0 plus Rayleigh Randall, and then this is just k horizontal square times theta 0. And the next equation gives me sigma and then theta 0 and then W0 plus k horizontal square plus n square pi square times theta 0. So I can eliminate one of the theta 0 and W0 from this and then get an equation involving, basically I can take theta 0 from here and put this back here. And then the W0 will cancel out from the resultant equation. And I get some, and then let me simplify by saying Qn square is k horizontal square plus n square pi square. So this is
something with the signs.
the
These
signs will cancel, right?
no, because lambda square will get a negative sign, but lambda to the fourth not.
Yes, of course. So this may have a negative sign.
And there's another one on the right hand side. Because this was another square. Horizontal.
Right, the last one. The last one. Yes. Thank you.
And in the second line, there's
Yes.
again one.
And in the second line, there's second one. Exactly. Thank you. I would have landed up in a place if I didn't get correct this. But nevertheless, so theta 0 is W0 by sigma plus Qn square. I put this back on the right hand side, which cancels W0 from everywhere. And then I get an equation which looks like this: sigma square plus So this is my dispersion relation. So this is how the growing mode is related to the horizontal and the vertical modes, where Qn square contains the horizontal mode plus n square pi square. Okay, so that's it, not too bad. And then one can show that in terms of n, which is basically the z-dependent quantum number, or which basically says that how fast it is varying along the z direction, the mode which first grows unstable is the n equal to 1 mode. So let's concentrate on n equal to 1. And let's forget about higher ends for the time being. So let's say we concentrate on n equal to 1. Okay. So for this mode, one can find that there is a critical Rayleigh number, which is pi square something like this. Right. Okay. I think so. Because it has to be the critical Rayleigh number. Actually, no. That I have a bit of doubt about. But anyway, it doesn't matter. So then one has to, for example, think about the following. So if we make a plot of the Rayleigh number as a function of the critical Rayleigh number as a function of kh, we typically get a plot like this. So this has a minima. The minima corresponding to this is the critical mode. So you see what we are doing. So we look for a solution of this so that sigma is 0. That gives me this equation. Now then I see how this critical Rayleigh number depends on the horizontal mode, and that gives me the most unstable horizontal mode. So mentally, I am increasing the Rayleigh number. So for the lowest, but this is the point where at least one mode becomes unstable. So that is the critical point. Okay.
There's already several modes because this is only the modulus.
Exactly, exactly. And that is not an artifact of doing a linear analysis, because we have rotational isotropy in the plane. So we are bound to have a mode which is basically a band of modes. The other thing then is to also lot sigma as a function of k. So the important part is where sigma is 0. So you'll have something like this for when the Rayleigh number is less than the critical Rayleigh number. At the critical Rayleigh number, so this is how we imagine things will look like. We can actually take this equation and actually find out exactly what those curves are. And so again, this expression I am just pulling out of my hat. So slightly above criticality, we have an expression which is like this. So important thing to note here is, what are we actually finding? So clearly this will be the maxima. The critical wave number for which this is true will be the maxima of this curve. So as this is the maxima, near the maxima I can always expand it like a parabola. So you see there are slowly some generic features coming out of the problem. Once we want to write the growth rate as a function of the Fourier mode, near the criticality we can always write it like an inverted parabola. Okay. Also, this tells us that near the criticality, so if it is an inverted parabola, then basically there is a whole range of band of modes here which are going unstable. And they will start interacting with each other to determine what is going to happen to the system. Now the important point to note is all other length scales have kind of become irrelevant in the problem. Have become irrelevant in the problem. Are no longer important. All other length scales. Because this is the length scale around this Fourier mode and its neighborhood that is important. And also we now know that we have a growing solution, which is the sigma. The sigma is the growth rate. So we only need to look at time scales which are slower by that factor. So now to do an expansion like what we did before, let's first take our small parameter. And the obvious small parameter is Rayleigh minus the critical Rayleigh number. And let's call that epsilon. Now the growth rate one can actually show for this problem is actually proportional to this. So, which is again epsilon. So you see this is exactly like the problem of the van der Pol oscillator we were doing. The growth rate there also was proportional to epsilon, the small parameter. So this basically means that we can again transform time in the following way.
The factor of gamma
Yes.
might not depend on epsilon.
We will see. We will see.
But it needs to depend on epsilon.
It need not actually. What the factor gamma depends on basically is the second derivative of this curve, the curvature of this curve.
But if we want to have that sigma is proportional to epsilon, then we need to have it in both terms. In the constant term, this is already there, and it needs to be in gamma then too.
You mean this one?
Yeah.
No, this is in the bandwidth of the case, which is small. The bandwidth of unstable modes is small.
So basically, as I'm
Yeah, but the quadratic term is necessary, otherwise you don't get any sigma that is positive.
you are worrying about this one, right? You are worrying about this one, right? I'll come to it. Just a second.
Okay.
So let's now first worry about time. So that's how time should scale. Okay. At the same time, what this one tells us is that K minus Kc is actually like this, right? Because this is square root of that. So which basically means that space should scale like this. So just to make life simple, we can replace square root of epsilon by epsilon, and then the scaling becomes epsilon square okay. Okay, so we have the scaling we want. We then just need to put it back in our full nonlinear equation. We need to put it back in our full nonlinear equation and then do exactly the expansion I have done for the simpler problem. Collect terms order by order, but now we kind of know what to expect. We know that if we are in the 0th order, we will basically get the linear equation. So, and it's easiest to actually do it in terms of stream functions. So it's actually easy if you take these equations, but use stream functions in the xz plane, which is the plane where we are plotting things here. And then the velocity is actually this is just because dealing with scalar quantities is easier than dealing with vector quantities. And then so basically these are completely equivalent formulation of the nonlinear problem. So you just put it back and then do the usual expansion. So and usual terms, put everything there, expand, collect terms. Probably there should be a mathematical program which should do this, and that will make things much more easier to expand and collect, and then do the scaling. And then we know, now we kind of know that to the 0th order in epsilon, we should actually just get solution of the linear problem. So we should have 0, so there is an amplitude which depends only on the slow variables, and then there is an exponential term which depends on the two fast variables. Actually this is I k x, where x is now x vector is x or y. This is the critical mode, and this will also have, I think, I z pi, because this mode corresponds to n equal to 1. But just to be in full generality, we can take x to include x, y, z, and kc to include the critical mode in the horizontal plane, and the n equal to 1 mode in the vertical plane. So this is what it should look like.
Can I ask a question? So
Yes.
since there is the direction of K, I mean, the stable modes make a
Yes.
circle, so why don't you start with a linear combination of various unstable modes for all lambdas?
That is what we should do actually. But then once you write such an expansion, we also have to demand that how we are combining them should actually give us a real number on the left. And that's the only constraint. So that's basically, I'm just trying to keep it simple here. But that's what is done actually. So let's, for the time being, ignore that there is any x dependence. Let's, for the time being, assume that there is no dependence on the slow space. And go to the next order. And at this order, we again look for the solvability constraint. And the equation we get is exactly the same. Where now beta, of course, has a different expression. Here it was actually half. Okay? So mu is
So why do you include the term rows inside zero?
which one?
Because so you write sigma c, and sigma c is a small number.
Sigma c is not a small number. Actually, it is. Yes, it should be there.
Using the analogy from the previous problem.
From the previous, yes, from the previous problem we actually had omega naught there. Doesn't it?
Yeah, so it was just oscillating.
Yes, it was just oscillating.
So the linear order is oscillating, and then the growth is
But
included.
here the linear order is not oscillating. The linear mode is not an oscillating mode.
So it's also growing.
It's just a wave mode. So we just have that. Basically. Yes. Okay, now, okay, so I think I have gone through all the stupid part. So now basically one can then say, okay, now now what we will next do is we basically will stop doing any calculations and just write down equations like that. So one of the things we could always write down for such an amplitude equation was a term, I'm sorry, this is wrong, of course. So what we could always write down was a term like this, the linearly growing mode. Because we are at a slow time scale, at that time scale it will grow like this way. That's kind of obvious. And then it has to saturate somehow. So let's now invoke symmetry. For this problem, you can actually say that there is a symmetry going from A to minus A. So then let us say that an equation like this is actually derived from some kind of a free energy functional. So we say this.
So this amplitude equation should be valid beyond saturation?
Yes. This amplitude equation, see, This whether they should be valid beyond saturation is a more difficult question.
But
They
this is
should be
valid in the linear phase.
kind of immediately after the linear phase. But longer,
Immediately after. Okay.
but longer you want to keep them valid. You see, this is the expression for the first one. There is a whole perturbation series in this. So longer you want to have them,
Longer.
the more number of terms you want to keep. But I mean the expansion has a real small parameter, so it's a controlled expansion. But I don't really know about its convergence properties.
So, I mean, what is the, when you say just after saturation and maybe not long enough.
Yes.
And it's also at the end of the linear phase.
See, a lot of things can happen now. For example, you see, we now have actually in this case, there is a whole band of modes which are becoming unstable. So those bands can interact with each other. So, you guys feel free to leave. This was mostly to bore Matthias and Pierre.
So aren't there here the two slow time scales, because sigma is small, so this is a slow time scale, and t belongs to a slow time scale again.
The small t is a fast time scale.
I see, but I speak about the capital T.
So
if I look there, at this ansatz for psi,
so actually this 2 gives an order 1 number.
it's order 1, that's 0. Yeah.
This 2 gives an order 1 number.
And t is
And
large.
so actually does this 2.
It's the
It's
fast.
a small t, yeah, I see.
Yes.
So what does it mean?
And the capital X is also for smaller scales, or no,
No, slower, larger scales.
larger scales.
Larger scales.
So it is assumed that the saturation happens slower than the growth. Yeah, of course.
Yes, of course.
Yeah, that's fine.
Okay. Now basically the interesting part comes in. So let's say we try to write a free energy function, which is here. So if we just want an equation like this, then we can say what that would look like.
This is what you had written in that notes, right?
Just this, right? So a functional derivative of this with respect to A will give me exactly this term.
It is this A E star square.
Yes. See, a functional derivative of that will give me this one.
Oh, okay.
Right, so this is just what I'm writing from here. I'm kind of reverse engineering it. And then I can say that I could have actually written the first term down immediately by saying that there is a symmetry between A to minus A. So the first term that the Lagrangian can contain must be proportional to A square. And then if there is a symmetry going from A to minus A, the next term the Lagrangian can contain will be, of course, this.
Fourth order.
Yes, because there can be no cubic terms. And these two must come with different signs if this one is to saturate this one. So immediately I can write this out. So this form of a Lagrangian is kind of generic. If there is a symmetry between A to minus A.
But we have no theorem saying that there must be a Lagrangian.
No, but you can always write it as a form of this. I mean, if there is an amplitude equation which is valid, then it can always be written in this form. And if there is a symmetry between A to minus A, this is the only form it can take.
And can it really always be written in this form? Because we have to deal with the interaction of many modes.
Yes. So a lot of things can happen. For example, for a peculiar system, you can have beta equal to 0. For example. Because we don't know what beta is if we put it by hand. And then we must look for higher modes. But some things are generic. For example, it is generic that this will be a square root term.
Should we still record?
It doesn't matter.
So you have more equations?
Yes, but I have all things scanned in.
So I think what we can do is we can formally stop the talk and then we can
No, you can
continue
just
about this.
stop recording and
About
I
this
can keep talking about
paper. Because there was this type session anyway.
yes, but it will take a little while to still.
Oh, okay. So it's not over. Okay, then.
But we're almost there. So what I'm saying is basically that this is very generic. So one can write the Lagrangian depending on what are the symmetries of the problem. You can just.
We don't know whether there is a Lagrangian. If you speak really about the interaction of many modes.
Yes.
Do we know that there is a Lagrangian necessarily?
One can, okay, so let me see. Even if there are many modes, the modes are growing unstable only in a band like this. Because that we know. And we know kind of roughly what this scaling is.
Sorry?
What this scaling is. Because we know that will be square root of the epsilon. So then rest of the analysis just goes through. There is.
But we then have
So
several amplitudes. You have not only one amplitude.
Yes.
So what are you asking? You're asking that how can we write a Lagrangian for a single mode?
Isn't there a Lagrangian necessarily?
But any problem should have.
Why? Where does
kind-
it come from? We speak here about amplitude equations, not about this fundamental physics.
No. Here, this says that Lagrangian form has. See, when typically in mechanics to write a Lagrangian, you talk about Hamiltonian systems.
Yeah.
This is not a Hamiltonian system. This is a distributive system. So in that sense, saying that there will always be a Lagrangian is not valid here. But the thing is that the whole machinery actually goes through assuming some very simple things. For example, assuming that there is a minima here, which is always the case. Of course, it could be something like this. Then there can be two modes with different k's which are growing unstable. And then you will have this plus a b. And kc1, kc2. So, but as long as there is only one unstable mode, it will have only one amplitude. Okay. So, now that we are almost there, actually I don't need any more picture record, but anyway. Okay, so you see in that sense it is very generic. If there are many modes which are growing unstable, then there can be A, B, C, and
we need two. The two with the opposite velocities.
right. But there is another beauty. The other beauty is that there will be an additional symmetry. The additional symmetry will be that under parity, mode A will go to B, and under parity, mode B will go to B. Also, under parity, the Lagrangian will go to itself. So, if that is what we assume, then we can add a new term.
Yeah,
That's it. Okay. Now you start with this Lagrangian. You have two equations, one for dA dt and one for dB dt. These two mu's must be the same because they must have the same growth rate. Otherwise, one will dominate.
yeah, of course. These two equations must be completely complementary. When exchanging A to B, they must
Yes.
revert to the other one.
So now the asymmetry comes in. So in principle, this is the one that can have the competition between one another. And then, okay, but we are still not completely there. The other thing that is remaining is, once I went somewhere here, after this I said, let's drop the dependence on x. So now if we add a dependence on x, the first thing that can add a dependence on x in the Lagrangian will be something like gradient of A and then square, because the Lagrangian has to be a scalar and things like that. If you add such a term, it will add a dissipation. It will be some term. Now this is actually very, again, now you have diffusion term in it, in these equations. So in principle, one domain can eat into the other domain. And in principle can show all the kind of valid behavior that Axel's biological equations show. But now important things are here, for example. Now, let me specialize to our problem. So I was, so the primary thing before we do any of this is to actually do a linear stability analysis. And the linear stability analysis is already done by our friend David. And what he says is this. So he is doing okay, so this is stable.
Now you are talking about the magnetic buoyancy.
Yes, now I am talking about the magnetic buoyancy stability. But it doesn't matter, the same equation.
Yes, same, or something quite similar.
Only that now we don't know what mu and beta are. But then we know exactly what mu and beta should be if we know the linear problem. But to actually find out mu and beta from the linear problem, we have to do this whole expansion in epsilon, collect terms.
But he also he has already done it.
He has also done it, yes.
What is eta?
Sorry?
Eta?
Right, eta is magnetic diffusivity. Okay, so he is saying these are stable, this is unstable.
What? This is strange thing to okay. Divide z of L. Oh, this is that same thing you have confused about.
And this is oscillatory. Okay.
What is the dash? Dashed one is oscillating.
No, here is oscillatory, then there is a transition from oscillatory to unstable mode in principle.
It's oscillatory with stable amplitude? No.
Yes.
But this must be marginal. Marginal. It cannot be in the range.
So that basically means we will have traveling waves into the problem.
But they must be damped. Except you are at the marginal point, but this cannot be in the area of this diagram.
Yes, but I think they are damped or not depends on what eta is.
Right, but then if they are not damped in a constant amplitude, they need to be a line in this plot, not an area. You cannot have a constant amplitude or not undamped in a whole area. I would not believe that.
That I think we have to look carefully at his linear stability analysis. But I'm just taking his results. So from stable to oscillatory, that will be a half bifurcation. Maybe with the oscillatory there is also a linearly growing mode. So this will be a half bifurcation. So that will mean that the beta here is complex. For this transition, the beta here is actually fully real, because there is no oscillatory mode. For this one also, the beta there will be complex.
Oscillatory means marginally stable always.
That's what he says. He says overstable. But basically it means that the eigenvalue has imaginary part. So this is for one set of parameters. I think this is for he also has a kind of Rayleigh number into the problem. Basically, there is a parameter which he calls R2, which contains the Brand-Vassala frequency and things like that. And this is for this one greater than some critical value. If this is less than the critical value, then there is only this two. And this is then stable, this is unstable, and this is oscillating. So one thing we need to do is to find out where exactly are we in this parameter space. And then we need to see how exactly we are going unstable, where in the parameter space. That will kind of put constraints on the equations, the Lagrangian equations that we are writing down. But other than that, there is nothing. I mean, we can very easily say that we can just take beta and mu from his amplitude paper. He did a finite amplitude calculation.
In fact, sorry.
He did a finite amplitude calculation. They can just take it from them. It may be a good idea to check them, but that's a different thing.
But what is the purpose of his paper? As in, he has solved this.
This one was linear stability. This one was just linear stability.
But does he find he finds one bifurcation there from stable to oscillatory, which
Yes.
he says, and not that.
See, from this diagram, you can't really talk about bifurcations. From this diagram, you just have the possibility of having bifurcations. But it's the amplitude equations which will tell you exactly what kind of bifurcation it is. See, it may be that you have such an amplitude equation. This kind of what